about compiler design in BTech course. Compiler design, Horn-Ullman is the prescribed textbook for compiler design. That is the only textbook which will include all the syllabus. And compiler means in first year also you people will execute C programs and all those things by using compiler, right? Stop. Hi everyone, today we are going to discuss about compiler design in BTech third year subject. Horn-Ullman is the prescribed textbook for compiler design. While executing C programs, you always compile that particular program that you have done it in the first year, right? So what you did exactly, C is a high level programming language and you wrote that program in C, and after that you compiled that particular program, right? But you don't know what exactly happens while compiling the program. So that's we are discussing in this particular subject. Okay, so compiler, what exactly compiler is? While going to your first year C programs, when you are compiling that particular program, what exactly you observe? You might observe that after compilation you got errors. That you can understand, right? So what exactly happens inside is the compiler will check all your statements, each statement, and it will compile all the code and it will verify whether it is having any syntactical errors, grammatical errors. If any error is there, then it will display that particular error with that particular line of error number, right? Lines of code. So that will happen while you compile that particular program. Okay. So the compiler, actually first of all you need to understand what is translator. Okay, translator itself is a program which will convert source program to target program. Okay, translator will convert source program to translator program, and there are three types of translators. First one is assemblers, second one compilers, and then third one is Good morning everyone. Today we are going to discuss about compiler design in BTech course. Compiler design, for that compiler design we have Horn-Ullman as prescribed textbook. Horn-Ullman is the prescribed textbook for compiler design, and the prerequisites for compiler design is you must know the flat subject and then a bit of OS and CO also you need to learn this particular subject. The course outcomes are, when you study compiler design, after end of this course you can write your own compiler. So that is the outcome of this particular subject. Okay, so compilers you might use in first year while you compiling the C language programs, right? So first of all, before learning what is compiler, first we should know about what is a translator. A translator is a program which will convert source program into target program. Okay, so there are different types of translators are there. The first one is assembler. The second one compilers, and then the third one interpreters. Okay, a translator will convert source program to target program. While coming to the assembler will convert assembly level programming language to machine level programming language. This is the task of assembler, which will convert assembly level programming language to machine level programming language. And then if you see compilers will convert high level programming language to assembly level programming language. Okay, compiler will convert high level programming language to assembly level programming language, and the interpreter will convert high level programming language to machine level programming language. Okay, so almost compilers and interpreters both will convert high level programming language programs. So in general what we will do is we will write programs in high level programming language. Why can't we write programs in machine level programming language? Machine level programming language will have only zeros and ones, right? But we always prefer to write programs in high level programming language. That doesn't mean that we can't write programs in machine level programming language. We can write, but it's difficult to write the program, right? That's why we will always choose high level programming language to convert a high level programming language. After that, the system will only understand machine level programming language. So that's why we will use compilers and interpreters to convert that particular high level programming language to low level programming language, which is machine level programming language. Both compilers and interpreters are almost the same, but the difference is compilers will convert the entire program into machine level programming language or assembly level programming language. Okay, but interpreters will convert line by line. Line by line it will convert. Okay, that is a major difference between compilers and interpreters. But in general, compilers will convert high level programming language to assembly level programming language only. But while you did it in the first year in TC and GCC, it will have entire thing. So it will convert high level programming language to low level programming language only, I will tell you. Okay, so what will happen is exactly when you did your C programming, first of all you will write the C program in high level programming language. That will be given as input to the preprocessors. That will be given as input to the preprocessor. Okay, from preprocessor you will get pure high level programming language as output. So what is the difference between high level and pure high level programming language? The difference is in high level programming language you will always write starting hash include, hash define, all those things will be there, but that code will be linked later, right? But in pure high level programming language that code will also be included in the program and that will be given as input to the compilers. So the compilers will get pure high level programming language as input. Okay, and the compilers will convert pure high level programming language into assembly level programming language. Okay, this is the task of compiler. Next, assembler will take care of this assembly level programming language. And here relocatable machine code. Machine code will be the output of assembler. From here, linker or loader will take care of the remaining things. Okay, the loading and linking things will be taken care by the linker and loader, and you will get machine language executable code. Machine code will be generated here. The executable code will be generated at the end of this phase. Okay, so what exactly is happening? First of all, the high level programming language will be given as input to the preprocessor, and preprocessor will take care of hash include, hash defines, all those kind of things, and that code will be inserted in the program itself, and that will be given as input to the compilers. And compilers will convert the pure high level programming language as taken as input, and it will generate assembly level programming language. And the assembler will take care of this assembly level programming language, and that will convert into relocatable machine language code. That will be given as input to the linker and loader, and finally we will get machine code as output. Okay. So actually compilers means it will convert pure high level programming language to assembly level programming language. But if you see GCC and TC everything, that will do everything. This preprocessor, compilers, assemblers, everything will be done, and we will get output as machine code. But in this compiler design course, we are going to learn about only compilers part. That means the input to the compilers is pure high level programming language, and the output will be assembly level programming language. Till this, only this part, the pure compilers part only we will see in this course. Okay, so next, there are different phases of compilers are there. There are mainly 6 phases of compilers are there. Okay, so the first phase is lexical analysis phase. So what we will give is, we will give one particular statement, the program as input to all these phases. So first phase of the compilers is lexical analysis. In this lexical analysis, it will remove all the comments, all the spaces, all the white spaces, and everything will be removed in the lexical analysis phase, and it will convert that particular program into stream of tokens. Stream of tokens. It will convert the particular program into stream of tokens, and it will remove white spaces and then comments and spaces and all those kind of things will be taken care by the lexical analysis. This is the only phase which sees the program as a program. After this, we will see the program as stream of tokens only. So after lexical analysis phase, syntax analysis is the second phase. As I already told you that the program will be seen as a program in lexical analysis, and it will scan each and every line and every word of the particular program. So that's why lexical analysis will also be called as a scanner. And syntax analysis is the second phase of the particular compilers, and the input for the syntax analysis is stream of tokens, and the output will be the parser. Parser or syntax tree. Parser or syntax tree will be the output of the syntax analysis phase. Syntax analysis will also be called as a parser. Okay, so next, after converting it as parser, that will be given as input to the semantic analysis. That will be given as input to the semantic analysis. Here semantic analysis will take care of typecasting and all those kind of things, and it will generate semantic tree as output. Semantic tree or parse tree, in some books it will be called as parse tree also. After that, that will be given as input to the intermediate code generator. So for intermediate code generator, the input is semantic tree, and there are many forms of intermediate code generators, but the popular one is 3-address code. So in this entire compiler design subject, we will see the output of intermediate code generator as a 3-address code. Okay, 3-address code will be the output. Output of the intermediate code generator or the intermediate code, whatever, you can say anything. So that will be given as input to the code optimizer. So code optimizer will take care of removing the extra lines of code. If anything we can reduce, those kind of lines can be reduced in code optimizer for efficiency purpose. So after that, optimized code will be the output. Optimized code will be the output of code optimizer, and finally that will be given to the code generator. Now this code generator will convert this optimized code into assembly level programming language. Okay, so these are the main 6 phases of the compiler, and while seeing, when you executed C programs, you got so many errors, right? After compilation, if you have any errors, it displayed those errors. So error handler. Okay, error handler. So this error handler will take care of giving, showing all the errors of all the phases. So this will be connected to all the phases of the compiler. And not only that, for storing and retrieving purpose and all those kind of things, we need data structures. So here simple table will act as data structures. Simple table will act as data structures, and that will also be connected to all the phases of the compiler. Okay, so and first three phases will be called as analysis phase, and then the last three phases will be called as synthesized phase. Okay, so this part is analysis phase and this part is synthesis phase. Okay, so that is also there. So these are the main 6 phases of the compiler, and in some books there are 7 phases of the compiler is also there. That one is code optimizer will be before intermediate code generator, one is machine dependent and one is machine independent, that doesn't matter. Okay, let's see one example to see how it is converting particular program into assembly level programming language by using all these phases. So let's take one example as position is equal to position is equal to initial star initial plus rate star 60. So this is the input to the lexical analysis phase. Okay, so what we discussed, this lexical analysis will remove all the white spaces and all the comments and everything, and then it will convert that particular program into stream of tokens. Okay, so this position will be changed as ID1. Okay, so and then ID2, initial is ID2 and then rate is ID3 star 60. How you wrote this, whether it is identifier or something like that, you learned it in flat, right? So identifier means it will start with a letter and after that any letters or any number of letters or digits can be there, right? So like that, by using regular expressions you will identify whether it is an identifier or a keyword or a number, and then we will give those kind of tokens. Okay, so after lexical analysis, this line of code will be changed as ID1 is equal to ID2 plus ID3 star 60. Next, this will be given as input to the syntax analysis. So this syntax analysis will give output as a parse tree. So here equal to is the root node, and then left side one is ID1, and then right side plus and star both are there, plus I have taken as a root node, and then the left side of plus is ID2, and then next star we are taking operators as root nodes. Okay, so ID3 and then 60. So this is the parse tree for that particular input. Okay, so now we need to convert this particular thing into, we need to give this to semantic analysis. So next one is semantic analysis. So this will be given as input to the semantic analysis. Semantic analysis will take care of typecasting and all those kind of things. For example, 60 is there. So int to float. If we convert that, that will be taken care by the semantic analysis, and semantic tree will be the output of semantic analysis. So what will be the output? The same thing. ID1 plus ID2 star ID3, but here is into real conversion. Okay, so that will be done by the semantic analysis. Next, this will be given as input to the intermediate code generator. Okay, so by using temporary variables, we will calculate that particular variables. Okay, after intermediate code generator, what will happen? By using temp1, and we are multiplying the things. These two multiplied, and then I am taking one more temporary variable to add this with ID2. Next, we have taken temporary variable 3, and this temporary variable 2 is assigned to that. Next, we need to assign this temporary variable 3 to ID1. So now the result is stored in ID1. Okay, so first of all you can take 60 as temporary variable 1. After that you can do like this. Okay, you can have any number of steps here. So next this will be input to the code optimizer. Okay, here we need to remove, if any extra number of lines are there, then those will be removed in code optimizer. So how can you write this particular program? So you can take temporary variable 1 is equal to id 3 star 60. Okay, you are calculating. After that what you can do? Here after we assign temporary variable 2 to temporary variable 3, and after that we assign this temporary variable 3 value to id1. So this line of code is unnecessary line of code, right? So that's why we can remove this particular line. Next we can directly assign this temporary variable 2 to id1. So like that, if any unnecessary lines of code are there, then we can remove it in a code optimizer so that the efficiency will be increased. Next, this will be given as input to the code generator. Now this code generator will convert this particular lines of code into assembly level programming language. So how to do it? First of all, we need to assign the 60 value to register 1. Okay, so we are assigning this 60 to R1, and then next what you need to do, you need to multiply it with ID3, right? So multiply, F is floating point number, and then we are so in R1 we have kept as 60 as input to the R1, and then we need to take ID3. So and I am keeping ID3 in R2. This is also one. Okay, ID3 I kept it in R2, and then next we need to multiply these. We need to multiply R1 and R2, and the result will be stored in R1, Okay, so next, so now the result is in R1. So here the result is in R1. Next you need to add it with ID2. So I have taken R2 again to take ID2. Now R2 contains ID2. Okay. So next again add R1 comma R2. Now this entire result is stored in R1. Right? So now R1 is having addition also. Next that will be assigned to ID1. So move ID1 comma R1. Now the R1's contents will be shifted to the ID1. So now the finally after this multiplication and addition, the result will be stored in ID1. That's how we can convert the particular program into assembly code. Okay, sir. Now let's discuss about pass. We already discussed that 6 phases are there in a compiler. Not only phases, if you combine the phases, it will be formed as a pass. There are 2 types of pass: single pass and then multi-pass. Single pass means only one time we will combine the phases as a pass. In multi-pass, we can do it multiple number of times. For example, in single pass, there are 6 phases are there, right? First phase is lexical analysis, second phase is syntax analysis, next one is semantic analysis, and then next one is intermediate code generator, and then code optimizer, and then code generator. For example, you can take these 3 as one phase, one pass. These 3 as one pass. As we know that first 3 phases will be called as a front end and last 3 phases will be called as back end. Okay, so phases, if you combine the phases, that will become a pass. 2 types of passes, single pass, multi-pass. Single pass means only one time we will combine the phases as pass, but in multi-pass we can do it multiple number of times. That is about pass and phase. Okay, and next bootstrapping. There are 3 types of languages will be there. One is source language, second one is target language, third one is implementation language. Okay, so what our compiler will do, our compiler will convert source language into target language, right? What is this implementation language then? This implementation language is the compiler itself is a software, right? Itself is a program. So which language that compiler is written, that will be called as implementation language. For example, we will show this bootstrapping in T diagrams. Okay, so for example, let's take the source languages X and target languages Y. Here, what is this T diagram is showing? T diagram is showing that X is a source language and Y is a target language. So you need to convert X into Y by using some implementation language. For example, that implementation language is Ruby. Okay, so by using, that means this is the compiler written in Ruby language, and by using this we are converting X into Y. Okay, but does the system understand Ruby language? No, it can't understand Ruby, right? So you need to design one more language which will be understandable by the system. So next, for this Ruby language will be the source language, and what should be the target language? Target language should be the machine language. Now, for example, let's take C++. So by using C++, we are converting Ruby language to machine language. Okay, like this you can do it, but still C++ also won't be understandable by the system. So you can take C++ as a source language. By using C, you can convert it into machine language. But C also it won't be understandable by the system. So you can take assembly language to convert. Okay, but still assembly language also won't be understandable by the system. So what you need to do? You need to write it in machine language and you need to convert it into machine language. Okay, so this procedure will be called as bootstrapping. What we have to do, whatever language we are taking, you can use any language for compiler for conversion of source code to target code. But the thing is that particular high level programming language also won't be understandable by the system. So that you need to write one more compiler for that understanding purpose. Thank you.
Thank you, sir.